Okay, and Niels, we're live. Welcome everyone. Kubernetes offers immense power. I like the abstractions. I think they're great. They're extremely powerful. But out of the box, if you take Kubernetes, it's not always optimized for the specific needs of batch processing. So, and this webinar is all about sharing our experience and giving you some tips and tricks how you can optimize your Kubernetes cluster and make it more ready for batch processing, or at least making it more efficient. The next slide might be a little bit hard to read, but this is a little bit about giving you the context when to optimize and why optimization of a Kubernetes cluster for batch processing made kind of sense to us. So we have multiple customers that really run significant workloads. Just to give some numbers is multiple of our customers run over 500,000 core hours per month. So some of these customers are actually going towards 1 million core hours per month, right? Just the 500 core hours means 170 nodes running continuously. But you're doing batch processing often, like meaning you don't have 170 nodes running continuously. That means like even during the day, you can have hundreds of nodes actually starting up and scaling down while you're actually doing the processing. And just to give an additional number to this, we run for these same kind of customers, we run more or less about 1.5 million jobs per month. So given the scale of operations we're doing, any kind of operations actually makes a huge difference. It makes the user experience better, and most of all, it also reduces the cost.
Yeah, exactly. So small improvements here have a huge impact on the customer customers, but also you have an immediate impact on a huge amount of jobs.
Yeah. So what are the challenges we want to cover today? First challenge is actually talking about the inefficient node usage. So if you spin up a node, you're not using the full resources. That means like having a lot of waste, right? The second one, talking about the unreliability of actually using spot instances on public cloud providers. And the third one, talking about, we already briefly talked about it, like it's not that you're continuously in batch processing, you're running all your nodes all the time. It's very spiky. Kubernetes isn't always optimized for that, so we'll dive a little bit into these ones. Fourth one, but definitely not least one, is all about how expensive it can be when you have data shuffling across availability zones in public cloud providers. And last but definitely not least, it's when developers, and I don't want to bash developers, but once in a while they can do a poor job in setting the correct resource configurations. And there's just waste because they're either too high, either too low, and both cause issues. Niels, I think with that, I actually, the floor is more or less yours.
Okay, super. Yeah, so let's dive into this first challenge, which is called inefficient node usage. To give some context, as Pascal already mentioned, if you're using virtual machines to back your compute on Kubernetes, you say, for example, a standard node like on AWS, 16 gigabytes of RAM, 4 vCPUs. If you say, these are my nodes that I use for in Kubernetes, of course, not all those resources are available to run your workloads. That is because Kubernetes has a bit of overhead here. What are the two major sources of overhead? This is the node overhead, which is used for running your operating system, running kubelet, which is, of course, in charge of spawning up containers, pulling images, etc. And then some minimal thresholds to make sure that your VM runs correctly. So that's number one, the node overhead. The second thing is the daemon set overhead. Daemon sets, those are components that you as a Kubernetes administrator install on your cluster, and they will run on every node. This means that this overhead will be present on every node, so you want to minimize that as much as possible. What is left is actually usable for your workloads. So what are the ways to make your nodes more efficient? One way could be to say, well, let's use bigger nodes. Since this node overhead is not proportionate when your node increases, you could say, okay, the fraction of overhead from the daemon sets and the nodes is less if you use bigger nodes. And this is true. This is exactly right. The only downside is if you don't have enough workloads using that node, you might also waste a lot more. So it's a bit of a trade-off there between picking a node that you don't have too much overhead in and not wasting some resources because you don't have the number of workloads that can use it.
Mm-hmm.
So that's why in practice, if you run these types of clusters in production, you will have a mix of node pools. Some with smaller nodes, those run the small and medium-sized tasks that you have. But if you then need, for some specific Spark jobs, a lot more memory, a lot more CPUs, for those you will have custom node pools that can be used for these specific workloads.
Do you always choose a specific one, or you basically also have a default one?
Yeah. So that's what I say. You have different node pools. Typically, you will have a default one that's a standard that will be used predominantly for most workloads. But then for specific cases, you go out of that and you use a more specialized. It could be a GPU instance node pool, or it could be something like that,
Okay.
something else.
So summarizing, there's definitely some overhead. You don't get all the resources the cloud provider node actually gives you. There's some overhead in node overhead, daemon sets. Then you have where you can actually run your own workloads. And basically, it's important to actually choose a default kind of node pool and then combine that with specialized node pools.
Yeah, exactly. Okay. And that all depends a bit on what type of company, which type of workloads you're running. Okay. So now, given we have this node, the daemon set overhead is something you can tweak as well. The daemon sets, that's components that you run on every node. What are examples of this? Well, you have the default one that you need to run any Kubernetes workload, and the networking for local DNS, kubeproxy, also for passing through traffic, HTTP traffic, etc. That you can't do without. But then you have components you can decide as an administrator, we want to support this or not. Logging metrics, well, this is of course needed anyway, so you need to install this component, but also container storage interfaces if you want to attach block storage to your node, or you want to use it for mounting secrets in pods. Those you can add, but be mindful, well, if the amount of components increases, of course, also the storage, the resources they require increases, and the efficiency for your nodes will go down.
Okay.
And then the last component that is listed here is CrowdStrike or Microsoft Defender. That's typically an organization-wide decision.
Yeah. Niels, I'm going to interrupt you for just one moment. I think I figured it out what's going wrong with our presentations. I think can you now try and share your actual presentation instead of our backup slides?
Yes. This works better. Yep.
So apologies for that. I think it was actually my mistake. I clicked the wrong button. I had a question regarding this slide actually already going on. You say these things can be tweaked, but I know like these cloud providers typically also have like these add-ons which gets like pre-installed. Like, can these also be tweaked, or how do you address that?
So I think if you run a Kubernetes cluster on a cloud provider, the add-ons they install or the nodes that they manage, there you have little options to tweak it. But going outside and managing these components yourself or managing the nodes yourself, if it's allowed by the cloud provider, is not that difficult because most of these components are open source anyway. So the rule here is, if you're starting with Kubernetes, use just the add-ons as is. If you notice that there are some inefficiencies or you think you can gain something by managing it yourself, you can do that.
Okay, got it. Thanks.
Okay, so we now went over what is the overhead. We said, okay, we have our workloads. This is all theoretical. Huh? Now let's say, let's dive into some numbers. And we support both AWS and Azure. This is just to give an example. I used the example of an X large node. 16 gigabytes of RAM are available for vCPUs. If you subtract the overhead, what you have left on AWS, we have 14 gigabytes of RAM, and on Azure just slightly a bit less. But that's just to give you an idea on what is available for workloads.
If I'm not mistaken, not all nodes are created equally, right? I remember an issue with that.
Yeah, that's something we struggled with, or we puzzled with for a while. It's certainly on AWS is the case, since you have these different instance types. There are slight variations of a couple of 100 megabytes that one instance has more than the other, which caused quite some trouble.
Yeah, especially when you're optimizing and want to reduce the memory overhead of those daemon sets.
Yeah, then it might be that you're just over the limit and that a certain workload cannot be scheduled. That was tricky. So this is all theoretical. This is what could be available if you use it up to a maximum. Now, if you put this in practice, when we started rolling this out, we noticed that actually in practice, the efficiency is far worse than we expected. And the major reason for this is for batch workloads, you have these spikes, like Pascal already mentioned. We have spikes. Let's say you add 50 nodes, a large workload is running, it's finished. Now we have 50 empty nodes. By default, the Kubernetes scheduler for new jobs, it will favor the nodes that have the most capacity available. So it will favor all these empty nodes. But this contradicts with how we want to optimize our cluster. We want to delete those nodes that are not needed anymore. To visualize this a bit, you can use this graph, and you see that if you have an availability of nodes, as new jobs come in, it will actually try to distribute it evenly over all the resources that are available. But with batch workloads, we cannot delete simply one of these nodes while there is a job running, because that would fail the job, and that will not be a very reliable system you could work with. So the question is, what can you do? How can we improve this? And actually, Kubernetes has a quite a good way to do this, and that actually means you run a custom schedule. So the default scheduler, if you run it on a cloud, runs on the control plane, but you can just as easily run your own. And the custom scheduler, you can specify which strategy it should use. As mentioned, the default scheduler favors most resources available, but you can also use a strategy which is called the most allocated node. You want to pack as many jobs as possible onto one node before going to the next one. To visualize this, you can look at the next GIF. And you can easily see that after a big scale up, this works a lot better to scale down your cluster, because new workloads will be packed together instead of spread out.
Can I kind of summarize like the default scheduler that typically comes and how it's configured? That comes with AKS and AKS, all right? The cloud Kubernetes cluster. It's really optimized more for web application and microservices. But and it makes sense because you want to distribute things, like if a node dies, one remains up, so there's some contingency there. But for batch processing, it makes less sense, right?
Yeah, we want to be more aggressive, at least, and that's mainly just from a cost perspective. Okay. If the node is not used, we want to get rid of it. Because of these big spikes, we need to be more aggressive than in long-running jobs. Indeed.
And if you see those big numbers we're running for customers, 20% is a massive gain.
Yeah, so 20% difference it shows a small figure of the moment when we enabled the new our own custom scheduler or not. You see that we go from our default node pool from an efficiency of around 55 to about 75, and that's quite a big impact on both costs and also it reduces the amount of nodes that you're managing in your cluster. So how do you do this? I said installing a custom scheduler, and for the rest, it's just in your specification of your job, you specify what's the scheduler to use. So it's quite easy to enable, and it can give quite a big cost reduction.
Oh, cool. Thanks, Niels. Before we actually start with this one, let's add on to interaction, and I do want to know, like, how many people are actually using Spot instances at the moment for data processing? So for now, we have one answer, and he's not using it. We have more people using it, not using it. So the majority is, for now, not using it. This is slowly shifting.
Okay.
What we see is Spot instance barely being used in production, being used slightly in development, but most are actually not using it. Let's give it a couple more seconds to actually get some more results. But I don't think, like, looking already at these results, it's not going to change that much anymore.
Oh, very interesting. Yeah, very interesting finding.
So I'll share those results as well. So you should be able to see them. So we see actually 74%, almost 75% is not using spot instances for data processing.
Okay, cool. So why would you use spot instances, or why do we think it's a good idea to use spot instances? So first of all, it's from a cost perspective. Most cloud providers, they charge 70 to 90% less for spot instances than on-demand instances. Why is this? Because it's basically they're selling their excess capacity. If they need it for some customer, well, they might take that node. So it's unpredictable for you to say that to know how long this node will be available. So that's also the issue or the difficulty with it. You're not certain that your job will finish because it might be that the node gets reclaimed. But for short batch workloads, this has a huge impact. And if we look at our customers,
can I first ask another question? What's short, Niels? Because you mentioned short, but I think you have to be a little bit more specific.
Short, I would categorize as, let's say, max 2 to 3 hours.
Okay.
That's what I would call short. Not days on. That would definitely not work well. But everything less than that could fit well on a spot instance. Of course, not if it's critical. That's a different matter. If we look at our customers, so I took an average of some of our customers where we looked at 1.5 million jobs a month, like Pascal mentioned. We have Spark and non-Spark workloads. I just made the distinction, but actually for spot usage, there is not a big difference. The vast majority uses Spot for everything. Of course, this encompasses both production and non-production workloads, but in general, our users, they prefer the Spot nodes over on-demand, and we'll talk about maybe how we make it more reliable than it is by default, or which measures that we take in order for Spot instances to become a better choice than on-demand.
Okay, cool.
So first thing you want to do if you're using Spot is, of course, reduce the likelihood of having a Spot interrupt. So that means that your job would fail because the node gets reclaimed. Our maximum at our customers is that 0.2% of the jobs fail because of a Spot interrupt. But that's a maximum. What are the ways in which you can influence this? I already mentioned shorter jobs reduces the likelihood. Another way is AWS has the Spot Placement API. It's actually an API that allows you to query, given I request these resources, what is the likelihood that it would be interrupted, that my node will be interrupted? And it will give a score from 1 to 10. Everything below 5 is quite poor, so the likelihood is quite high. Everything above 8 is quite good, and then you're quite safe. So this is an API that we use for in various places, just to make sure that we can use the right instances. Another big differentiator, if we compare our customers, is the region in which you run your workloads. And we, for example, have customers in Ireland and in Paris, and we see that in Paris, the likelihood of a spot interrupt is a lot higher than in Ireland, just because the capacity is less there. And then a last point, which influences it, is which type of node that you use. We talked about the standard default node pool, 16 gigabytes of RAM, 4 vCPUs. We see that there's an abundance of those. If you go a lot higher and you say, I want 10 times as much memory, the likelihood of having a spot interrupt becomes a lot bigger because there are just less of these nodes. If they need to be used, then you're out of luck.
Yeah, no, absolutely.
So this is how you can reduce spot interrupts. You can, of course, not completely eliminate them. They will happen, as also the figure shows. What can you do then? You can minimize their impact. Pascal mentioned that in our product, we highly integrate with Spark, and Spark has quite some nice tweaks in order to reduce the impact of a spot interrupt. One is one that we implement, and we say we have a setting which is called driver on demand and executors on spot. That means that all the executors runs on spot nodes, but the driver is kept on demand node. This has a huge impact because a Spark job then can handle executors dying. It will just spin up new ones as long as the driver stays alive. So this is actually quite a safe setting if you use Spark, which is also why a lot of our customers use it. The last thing, the Spark decommissioning part, that's purely a performance improvement. What this does is that if your cloud provider reclaims a node, it will move certain of its temporary state, its shuffle state, around to the nodes that will continue living on, and then you don't have to recalculate certain jobs. That's what that means. And the last point is, if it then happens, a spot interrupt, then make sure that it's very visible for users that this was the cause.
You're on a roll, Niels. No, so if I can summarize, this section is like we saw many users actually not, or many organizations not using spot instances in production, especially for batch loads. We think it's really worth it. There are ways to actually limit the chances of spot instances being terminated. If you run Spark on Kubernetes, you can run your driver on demand, and there are multiple things implemented by now in the way how Spark behaves on Kubernetes to actually make it fail gracefully and actually recover even when some of the worker nodes actually die. And last but not least, make it visible to users when this happens. If I'm not mistaken, a lot of our users also implement kind of a retry behavior. So if something fails overnight because of a spot interrupt, basically they just automatically retry. And then typically because of these spot placement score, you typically probably go to another AZ or another region, and then they recover in that way.
That's indeed the behavior we see often. Correct. All right, so that wraps up for what to do with spot instances. A third and major important topic is how do we deal with spiky workloads? And we've mentioned it before. We have in batch processing, you have quite spiky workloads. This just shows an illustration of an average customer of us. And you see that there is typically a factor of 10 difference between their lowest amount of usage for their cluster and the peak. So you see here it's between 40 and 350 nodes, and that fluctuates quite heavily during the day.
Yeah, you see, actually, we see it with most of our customers is that the most batch workloads happen actually during the night, right? And the moment they get into the office in the morning, all their data is fresh again.
Yeah, exactly. So how do you handle this kind of changes? Which components do you need? Typically, there are two that come to mind. It's a cluster autoscaler and Carpenter. So let's quickly dive into those, which settings you can tweak, how you can handle them. Let's start with the cluster autoscaler. This has been around for a long time. It's supported on all the major clouds. It's the one we use currently on Azure because Carpenter is not mature enough yet to run on Azure. And what are the things that we do here? Basically, the major change that we make to the settings is we are more aggressive in scaling down our cluster. That means we only wait 5 minutes if a node is underutilized to kill it. We refresh frequently to detect whether to scan basically whether a node is underutilized or not. Those are settings that you should tweak a bit. You should find out which setting works best for the workloads that you handle. Another thing which is quite useful if you use a cluster autoscaler is this priority expander. The priority expander is basically a setting. You see a small image on the right, which you can give priority to certain node pools and basically say, well, if you need to create a node, first look at this node pool, then look at another, then look at another. It's a very good way to make more complex or more advanced configurations if you have certain preferences.
Okay. Is one high or
100 is the highest,
okay.
And one is the default to make sure that every node per week provision at least gets a chance to be checked.
Thank you for the inconsistency.
So what are our lessons learned on, in this case, primarily using cluster autoscaler on Azure? Here again, we use our own self-managed cluster autoscaler, not the one that's provided by Azure, just mainly because some configuration settings that exist in the open source version, they are not supported to configure it through Azure. So that's why we manage it ourselves. We mainly talk here about some startup things, some more advanced stuff that we cannot use the default one. Another thing is actually not a Kubernetes related thing, but sometimes Azure resources have a very strict limitation on the length of the names, and that's why you see these almost unreadable names to have the right information there, but it has to fit in within 16 characters. It's stupid. And then a final thing is how to manage upgrades. Upgrades of a Kubernetes cluster running batch workloads is a bit more tricky than the default Kubernetes cluster because you cannot drain immediately your nodes because that would kill the jobs that are running there. So handling that is a bit more tricky. What we do is we create new node pools, we tag them that the cluster autoscaler uses them, we basically cordon the old ones that they are not used anymore, but the jobs that are running on those, they can still finish. And then after a day, the cluster autoscaler is all scheduled all new workloads on the new node pools, we can decommission those.
And that wouldn't work with the custom managed, like the Azure managed cluster autoscaler, right?
No, they do both in place. So they add new nodes and then they drain the old ones. But then the impact might be that the job fails.
You have interruptions then.
Yeah, and that's not what we want, of course. That would be a poor user experience.
Okay, so it means like if you really want to on Azure, on AKS, and you want to run batch loads there, and you want to have this efficient scaling, you should run your own cluster autoscaler.
Yeah, that's what we go to. Of course, I did see in the docs that they are working on changing these options, that we could tweak it a bit more, what should happen if you do an upgrade, but it's still in preview, and we still have to see how this rolls out.
Okay.
Second component, this is for AWS. If you run on AWS, is Carpenter. It's actually quite a recent one. It's been released, I think, 2 years ago. We've been using it the past 1.5 years. And it's a great improvement over using the cluster autoscaler. It's a lot more performant, more quick to scale up nodes, and it basically also makes our lives a bit easier. And why does it make our life easier? Well, mainly because the configuration is more flexible. You see on the right a specification of a node pool, and you see that you have some flexibility defining the instance type, but also architectures and both specifying spot and on-demand in one node pool instead of separating those. That's a small change. The more important thing, that flexibility that it gives us, is that it supports the price capacity optimized strategy for assigning spot nodes by default. So again, this uses in behind the scene AWS APIs, and basically it says it favors spot nodes that are cheap, but also with high capacity. And that means that the likelihood of a spot interrupt is again lower. And that's what we want. Before using Carpenter, we were doing this manually, and we had a lot more code to make sure that we choose the right instance type. Now Carpenter does this all for you out of the box.
Okay. You mentioned they're working on a version for Carpenter for Azure.
Yeah.
But you're saying like, don't look at it yet, it's not ready yet.
Yeah, for us, it's not production ready yet.
Okay.
But they are making good progress. I see the last couple of months, there are quite some changes made, but not good enough yet to roll it out to our customers. Some small attentions and things that we noticed. Carpenter has a lot more aggressive consolidation, which basically deleting nodes settings than the cluster autoscaler. Something to watch out for. And that's also the reason why we use the when empty strategy. Again, only remove empty nodes, not underutilized ones. And then the last one is maybe a small anecdote, is it's always good to have a lot of instance types that you support for a given node pool. Right? The instance types, they are shown on the right. I have here the 7th generation of Intel and AMD listed. We initially used only the latest generation to make sure that we can use the most performant ones, but at some of our customers, they use this many workloads that basically Carpenter couldn't schedule new spot nodes because there were no instances available anymore of that type. So this is just to make sure, add a longer list to make sure that at least you find a node, even if it's a bit less performant.
Yeah. So differentiate.
Yeah.
Right.
Exactly.
So to summarize this topic is on Azure, use the autoscaler, but tweak it so it scales down faster when you want to do batch workloads. On AWS, use Carpenter. It has many settings. It has all these kind of like optimized price capacity, optimized allocation stuff going on. That really helps you to manage this efficiently and handle actually these spiky workloads that you typically see in batch processing.
Yeah, exactly.
Cool. The next topic is actually expensive cross-AZ data transfers, and you know why I'm smiling, right?
Yes.
Because I actually 2 days ago at a customer, they were showing me their AWS bill, and indeed, like they had a major migration going on, and they were complaining like, why is our network cost so high? I thought, yeah, it's probably going to be like cross-AZ data transfer. You missed something. They're not running Spark, they're running Trino. but they have exactly the same. And I also advise them on how to solve that. But I'm gonna let you tell the story how to solve this one.
Yeah. So this was something we experienced at one of our largest customers. Of course, we set up our Kubernetes cluster to be able to spawn up nodes in different availability zones, to be able to handle an availability zone going down. So we set this up, but one of our customers who runs a lot of very big Spark jobs, they saw indeed also a huge spike in their network transfer costs. That's basically because Spark, the shuffling, moves some data around between these nodes, and if they're in different AZs on AWS, you need to pay money. I looked it up again, but indeed on Azure, since middle of last year, they explicitly say that they don't charge for this. So this is only a problem if you run on AWS. On Azure, this is not something you will encounter. So in order to fix this, what did we do? Well, we basically decided when a user launches a Spark job, we decide which AZ to run it on.
Yeah.
This is again based on some algorithm. Well, the algorithm is quite simple. On demand, we just use a round robin. We just pick at random. But on spot, we use displacement score. And displacement score decides are there instances available of the one we want or not. So we can use this to leverage which AZ to run it on. We fix it for a Spark job. Fix it in the sense of set a specific AZ for a Spark job, which means that all the executors, the driver that will be spawned, they will run on that AZ. So technically, if you're interested in the operator, so our Spark operator decides it when it gets a Spark job in, decides what's the AZ that's best to use, and then for every podlet that gets launched, we have a mutating webhook, intercepts that request, and says, this is for this Spark job, so we set a node selector, you should use this zone. That's the technical implementation of Kubernetes. So it's not a rocket science, but it had a huge impact on the cost.
You put like a little wrapper around it, and you basically decide up front which one to target, and then basically you intercept everything later on to make sure that everything ends up in the same availability zone. It's not only about cost, right? Because the closer the nodes are together, you also get performance benefits.
Yeah, exactly. Indeed. It's also more performant. Network transfer will go quicker if it runs in the same AZ. Yeah.
Niels, I'm actually seeing like we're running slightly out of time. So I propose to actually skip point number 5.
Yeah.
I'm sorry, that's me messing up the presentation in the beginning where we lost some time. So can we skip to like the key takeaways? We'll share the slides later on. I do want to take a little bit of time to answer some questions.
Yeah.
So the key takeaways are basically Kubernetes. It's a great tool. Cloud distributions are actually great, but they're not a complete solution if you really want to optimize for batch processing, right? So the next point is you need workloads, right? If you want to optimize, don't do it when you don't have enough workloads, right? Don't boil the ocean. Don't go looking for trouble and optimize something where there's nothing to optimize, right? Then pick very much where to optimize, right? We showed you 4 dots and a half, and not really. We'll share the slides later on. So we shared a little bit like there are multiple spots where you can optimize, right? You can do it on networking, on scheduling, on node usage, on reliability, using spot instances. So there's a lot of places, and we hope we gave you some inspiration where you can look how to make this more efficient. And if you have a problem, look at open source solutions. Don't try to solve everything yourself. There are cases where you do have to solve it yourself, like what we did with the spot placement scores, like put a wrapper around it. But most of the time, like these tools like Carpenter and the Autoscaler and other tools, they're open source. Definitely look there.
Yeah. The ecosystem of Kubernetes is vast and it's huge and has all the necessary, tooling available.
Yeah. And last but definitely not least, optimization is an ongoing process, right? It's never done. I know currently you're working on some log optimization on Azure. That's going on. It's on one side it's time consuming, but the rewards are worth it.
Yeah, it's a great summary. I fully agree.
Let's see if we can answer some questions.